So today we are going to be talking about angular momentum. And this is the fourth unit that we're doing in this unit on angular motion. So we started out with angular kinematics, describing how objects rotate. We then went into torque and angular dynamics, basically the why objects rotate. We then continued with angular kinetic energy, which is another thing that needs to be conserved, similar to the linear motion kinetic energy. And now finally we are coming to angular momentum, which is another thing that needs to be conserved, just like what we saw with linear momentum and that angular kinetic energy, linear kinetic energy dichotomy. So let's go ahead and get started with this, with that example that we used last time of a mass on the end of a string that's going around in a circle. So we got this mass that's on the end of the string that's of radius r and angular velocity omega. So first we need an equation. And the equation that we've got for angular momentum is that L, and L is going to be the symbol that we're going to be using for angular momentum, equals the mass that's moving times the velocity, so that's basically the linear momentum, times the radius that it's operating at. Now, you might notice that these are both vectors, and that times in there is the cross product of those two vectors. For those of you who aren't that familiar with vector math like this, and dot and sign, dot product and cross product, you don't need to worry. But this is basically saying, hey, look, there's that sine theta in there if you're not having a 90-degree angle between the radius and the motion. We're going to keep that at 90 degrees for all of these examples. So we've got linear velocity and a radius in there. So let's go ahead and fall back on that equation of linear velocity is equal to the angular velocity times the radius, and go ahead and plug that in, and we end up with this angular momentum equals the mass times the angular velocity times essentially r squared. We know that our moment of inertia is equal to the mass times r squared, so we can do a substitution again and end up with the final equation that we're going to be using a lot for our angular momentum, and that's going to be angular momentum L equals I omega, our moment of inertia times our angular velocity. So, conservation of angular momentum, as I said on the top of this talk, is that angular momentum is a quantity that needs to be conserved. If we want to be all proper language about it, we could say something like, if the net external torque acting on a system is zero, the angular momentum of the system remains constant no matter what changes take place within the system. This is also true with the linear momentum. But now we're dealing with circles, and we're going to be doing things and be able to look at things maybe a little bit differently. So, to put this more formal, as in with the math, we've got that initial angular momentum is equal to the final angular momentum. So we can split that apart, and we get the initial moment of inertia times the initial angular velocity is equal to the final moment of inertia times the final angular velocity. We can rearrange this and get something that looks like this if we want it to, but basically what we're looking at is, hey, if you change that moment of inertia, your angular velocity is also going to be changing. No outside torques, no unbalanced torques necessary for us to have a change in angular velocity. All that matters is changing that moment of inertia, which we can do by changing the shape of our object. So how do we do that? What does this look like? And this is a prime example that we would do in class, is Sitting on a rotating stool, we could stick a weight in both hands, and as you pull that in, that's going to change your moment of inertia. So when you pull those masses in, your total mass stays the same, but the location, the radius of that changes. So that changes the overall moment of inertia and then allows you to drastically, in some cases, increase the angular velocity. This is the concept that's used in a lot of sports. For instance, figure skating, diving, and gymnastics all use this moving from a tight ball to a straight line in various different forms. For instance, tucking your arms in, tucking your head between your knees in gymnastics or diving. All of those are examples of changing that moment of inertia in order to change the angular velocity. Basically, spin faster. But what does this do to the kinetic energy? So this is the equation that we found last slide. And let's go ahead and plug that into our kinetic energy equations. So the final kinetic energy is equal to 1/2 times the final moment of inertia times the final angular velocity squared. We can do a substitution using that equation that we found on the previous slide, and it does in fact look like an absolute mess because there's a whole bunch of squares and subscripts floating around here. But we can go and cross out that one set of that final moment of inertias and regroup, and we end up with the ratio of that moment of inertia is equal to 1/2 times the initial states. And those initial states, well, that looks a lot like the initial kinetic energy. So let's do that substitution too. And what we end up with is something kind of weird in that our final kinetic energy is equal to the ratio of our moments of inertia times the initial kinetic energy. This means that somehow that energy is changing when you are changing your moment of inertia. This is weird given that no outside force is going on. How is that working? Essentially, what you're doing is by pulling in those masses, you are reducing your moment of inertia and increasing your kinetic energy. You must be doing some form of work. And this is an unusual form of work because you're moving the mass radially. So that's a force times a distance because you're having to overcome essentially that centripetal force in order to pull something in. You are going just more than keeping it out at a spot, which is the centripetal force that you would be using, but you've got to do more than that. You've got to pull it in. You've got to do a force times a distance, and that's going to be a form of work. So this seems like it violates the Newton's laws that we've been talking about, and it kind of does, because what we're doing is we're moving stuff in an accelerating frame of reference. A non-inertial frame of reference is the big 10-penny vocabulary word for this. So Newton's laws, as we know them, don't quite work the way that we would expect. But this all works as far as conservation of energy goes because you're doing work, and it works. No pun intended. So let's look at another example of how we can use conservation of angular momentum. And that's using this fact that direction matters. So one of the other demonstrations that I really like is to hold on to a bicycle wheel that's spinning while you're sitting on a spinny stool. And as you turn that bicycle wheel, the direction of the angular momentum changes. So because it's something that needs to be conserved and we're conserving a vector, that means that you have to be putting an outside force on that top rotating bike wheel if you're looking at that as being your system. So it needs a lot more of a force to move the bike wheel than you'd expect. Also, if you look at you and the bike wheel and the stool as a system, that angular momentum needs to be conserved. So as you do this, you end up starting to rotate as well. This is used a lot in gyroscopes, what's used in pointing satellites. In fact, when the Kepler mission, which was looking for all of the exoplanets, died, the reason why it died was because some of its gyroscopes ended up failing after they got to the end of their useful lifespan. It started with 5. They were able to use some backups, and eventually, once you got down to 2, you had to get very creative in how you were going to keep that satellite pointed. This is also the concept that your bicycle uses. So when you're going along fast, you are able to stand upright because that angular momentum wants to be conserved. The direction of that angular momentum matters. So when your bike wheel's spinning, it wants to conserve that angular momentum and stay in the same alignment, namely upright. It is much, much harder to stay balanced on a slow bike than it is on a fast-moving bike. This is a lesson that my father first tried to teach me when I was below the height that you could see with the video camera. It's not one that I believed him on until I started studying physics. So let's do an example with this. So a mass M is attached to one end of a string that's going around in a circle on top of a table. And the other end is in a hole in the table that's shown below. So it's spinning around, linear speed 2.4 meters per second, and then some joker is underneath the table pulling on that string, which is reducing the radius. So what happens to the speed of the mass? Angular momentum needs to be conserved. This means that that initial angular momentum is going to equal the final angular momentum. So we can split that apart. We get the initial moment of inertia times the initial angular velocity is equal to the final moment of inertia times the final angular velocity. And let's go ahead and split those moment of inertias out. So this is a case where all that mass is at the maximum radius. So the equation that we're going to use for that moment of inertia is the mass times the radius squared. You can probably notice that the masses will end up canceling, which is a good thing because it wasn't mentioned in the problem. And we can also go ahead now and split that angular velocities apart because the problem is talking about the linear velocity. So angular velocity, that's going to be the linear velocity over the radius. So I went ahead and split those both apart. And you can probably notice that a lot of these radii are going to end up canceling out. So if we hit that button, there we go, we start to see all those things getting canceled. So the squares can end up canceling out the term in the denominator. And what we're left with is something that we can solve for V final for pretty easy. So V final is going to equal the initial velocity times the ratio of the radii. Remember last time how I said in a lot of these problems you're going to have lots and lots of things cancel out, and that's okay. In many of these problems, lots and lots of terms end up canceling, which means that you can go from something that looks very nasty to something that's solvable. And if you end up thinking that you canceled too much, you can go back and check your work, but you probably didn't. So plug in some numbers in. 2.4 is our initial velocity. 0.8 meters is our initial radius, 0.48 is the final radius, and those numbers were chosen in order to give us a nice round answer of 4 meters per second. So, hopefully this is pretty easy for you. This is just one more term that needs to be conserved, and unlike in the kinetic energy where there was a whole bunch of other stuff going on top of things, this is pretty straightforward. So conservation of angular momentum is the moment of inertia times the angular velocity. From there, you should be good to roll, and I hope that you have the most excellent of days.